Today I would like to talk a little bit about the validation of requirements in the system modeling functionality. So basically what I would like to do is just to briefly talk about this feature, this future feature, um, how we're going to validate requirements with uncertainty. We're going to discuss also some application examples and a little bit of the language that we are working on to allow this to be used by users. So this is kind of the overview. First, I'm gonna give a quick recap on what system modeling is in the Wolfram language. Then we're gonna dig right into requirements and what they are. Then we're gonna see how we can already graphically validate some very simple requirements with functions such as system model uncertainty plot and system model plot. Then I'm going to move right into the functionality, which is based around the function system model validate. I'm going to briefly discuss maybe some of the validation language depending on the time available. And then I'm just going to go into the conclusions. Right. So just for a quick reminder, so the system modeling functionality connects to the system modeler tool. The models that you have in system modeler manifest in the Wolfram language as system models. By default, you already have the possibility to model all sorts of kind of domains, such as electrical, mechanical, fluid, thermal, mechanics, all sorts of these things you can already interconnect and create kind of interesting and complex models just by dragging and connecting components, like for instance, circuits, or you can go all the way to generating like a full model of a robot, like in this case. So why requirements? So requirements are basically conditions that your system must satisfy. Whether you work for a company or for an institution, there's a good chance that you have to satisfy some specific standards. This is the functionality that we want to offer. Requirements can be all sorts of things. Basically, it could be start from like physical requirements, basically just to check that your model is actually satisfying physical laws. Maybe it can be safety requirements or design constraints that are imposed by your product, or maybe they are performance requirements that are specified by the quality standards of your product. These are usually seen in the aeronautics industry or in electronics. For instance, a simple example of a requirement is in flight, when one engine is off, the air distribution circuit must provide nominal performance. Of course, these requirements can be complex in several ways. One of the ways in which they can be complicated is that they can insert uncertainty around time or the ordering of events. For instance, here we have an example for room heating modeling. So for instance, we have this one which says, whenever the heating is turned on, within 300 seconds, the room temperature must be in a specific range. So as you can see, there is another complexity here, that there is like a specified time delay. Because maybe your system has a specific an inertia, or maybe there's a certain uncertainty about how quickly your system reacts to events. So maybe you want to specify that explicitly in your requirements. Or maybe you want to say something like this. Another way in which requirements can be complicated is in this way. For instance, in this example, at no time the control signal should exceed a value for more than 0.2 seconds. So notice that here we're talking now about the duration of a specific phenomena in your system, which means another level of complexity in your requirements. But for the simplest kind of requirements, we already have tools that allow you to validate things graphically. For the more complex, you definitely want to explore a more elaborated language that allows you to express this in a nice way and also be able to validate any requirements that you may be interested in. So one way in which you can already validate the simplest requirements is by using functions just like system model uncertainty plot. Basically, this function allows you to specify a source of uncertainty about your system. You can specify that some inputs are uncertain. For instance, maybe you have a noisy disturbance, or maybe there's a tolerance in your parameters, or maybe the initial values in your system are uncertain in a specific way. But system model uncertainty plot does is basically it aggregates, it samples these sources of uncertainty and then produces several simulation results and aggregates the results in such a way that you can see what are the possible quartiles or the basically the confidence bands for your results. So for instance, if you have a requirement such that like this, a stabilized camera that is disturbed by a force must not move more than 2 centimeters. In the case in which you are modeling, for instance, a controller for stabilization of a camera, maybe you can, one way which you can already validate this in the Wolfram language is by taking your model of the camera stabilizer. Then you can specify uncertainty here by saying that you have this noisy force that is going to be represented here by white noise of a specific magnitude. And then you specify how many simulations you want to run, and then you can pass that directly to system model uncertainty plot. Then system model uncertainty plot is going to perform the 50 simulations with 50 different types of noisy forces, and it's going to give you the result for the position of the camera. And of course, you can plot this together with the bounds that you have established in your requirement. You have established that you want only 2 centimeters of um, above or below. And as you can see in this particular case, you are not fulfilling your requirement because you're going beyond these bounds. So this is kind of a quick way in which you can directly insert uncertainty, validate your models graphically, and then establish all sorts of interesting results for this kind of simple requirements. Another way in which you can already validate these things is by using system model plot. For instance, for the requirement at no time, the control signal should exceed 1.5. You can obviously, we have for a long time provided the functionality for you to just take a model and plot variables, but you can now also plot expressions. So you can plot together the variable that you're interested in and the bound, which in this case is 1.5. So you can visually see directly whether this fails or satisfies the requirement. But you can also directly specify the Boolean statement, right? You want this variable to be less or equal than 1.5. And then we're going to plot where this is true and where this is false. And then you can directly visualize this. So this is something that you can actually already do for very simple requirements and then helps you validate stuff. And in that same spirit, you can pass this, you can use also the function system model manipulate, which is a resource function. Basically what this function does is it creates a manipulate around the plots that you specify for the model. And then since this function is just simply using system model plot in the background, basically you can either plot the variable that you're interested in and then modify the parameters in your model, or you can directly plot the Boolean expression that you're interested in, your requirement, and then modify the parameter values and then see where they change. So this is another way in which you can validate already very simple requirements in your systems. But we want to go beyond that, right? The industry requires more complicated requirements. So that's why we have the function system model validate, and we're working on it. Basically, what it's gonna do is gonna not only be able to validate requirements with uncertainty, but also it's gonna be able to store these results so that you can report them. You can present nice results and analyze them and use them with the rest of the system model, Wolfram language functionality. But also we all want to cover all sorts of complicated statements in the language. So for instance, let's start with something simple. Let's start with a no time the control signal should exceed 1.5. So here I have my model. And here I have my call to system model validate. So system model validate is just going to pick either your model or your simulation results. And then you're just going to pick your requirement. In this particular case, what we're saying is we're passing directly the inequality. We're just wrapping it in something that in a function that we call temporal always, which is just going to ask for this to be always true. And then we just pass this to system model validate. System model validate in this case is just going to simulate your model and it's just going to quickly check your requirement. So the object that you get at the moment is system model validation data. It already tells you some of the results. Here it already tells you that there was a failure in the one simulation that we performed. You can plot, we can extract this property called failure plot, where it shows you where things went wrong. But you can also extract things that you can use for numerical computation, such as the failure intervals. So you can just specify here, you can get directly numbers of the times where this failed. And because this is the Wolfram language, you can use these things for to compute all sorts of things. You can compute the full time, the total failure time by just computing the length of these intervals, of these failure intervals. Or you can just plot the failure intervals in red, like this, with the number line plot functionality in the Wolfram language. So this gives you like a fuller report of where things went wrong. You can then go and check in your model where things could have been better. And with all this information, you have a closer and a better idea of how you can improve your model and also your product. Here's an example with uncertainty. So we go back to the example about this camera stabilization. This is the same exact requirement, but we're going to look at it from the point of view of system model validate. So we're going to specify uncertainty exactly in the same way. We're just going to say that there is a force disturbing our camera, which is a white noise process, and then we're going to specify that we want 50 simulations to check this. And system model validate is going to pick this uncertainty, it's going to pick the simulation specifications, and then you're just going to have to specify the requirement. In this particular case, we're saying that the position of the camera, we want it to be only at most 2 centimeters above or below from the original position, and we will just wrap this in temporal always, because we want this to be always be true. What system model validate is going to do is going to run the 50 simulations, check the requirement for all those 50 simulations, and then it gives you here already a result. So basically, it tells you that there were 17 failures. The success probability was 0.666. You can extract results from this as well. You can extract things such as the success probability. You can extract the failure configurations. So basically, you can specify how much information we store about the failure. By default, we only store results for one failure configuration, but you can, of course, store as many as you wish. And with these failure configurations, they're stored, we present them in a way that you can just pass them directly to system model plot. So you can just now take your model, pass your failure configuration, and say that I want to plot the position and the bounds. And then here you can see explicitly where things went wrong. Indeed, here the position of the camera went too high because of the force that we sent, which was in this form of this temporal data. You can also extract the success configurations. So maybe you're interested also in which forces didn't cause the system to break. So this is also a property that you can extract from the validation results. So there's a ton of other properties and all sorts of things that we want to support. I'm gonna now discuss a little bit about the language, because at the moment we have only presented very simple requirements, right? Mostly this kind of inequalities wrapped for something that we want to always be true. But requirements in practice, as we saw in the second slide, they can be very complicated. You may have more complicated temporal statements, temporal assessments. So I'm going to show you a little bit of the language that we're developing around them, this requirement validation, when you want to validate more complicated things. So the kind of things that we have is, I have already shown temporal always, which is just something that is going to ask you for the statement inside to be always true. We're also going to have something called temporal sometimes, which is just going to check it that it's true at least once. Then we have other more complex operators that are going to help you filter a little bit more the true intervals of your statements. So for instance, temporal becomes is going to focus on when something starts becoming true. So just the rising edge event of when something becomes true. Temporal between, you're going to be able to use it when you want something to be true for a specific duration of time. Maybe you want a minimal duration, maybe you want a maximum duration, maybe you want both. Temporal delay, so it's going to allow you to cover precisely the cases in which you have some time uncertainty. So maybe your system is just a little bit slow. You want to specify that in your requirement. Maybe you want to specify that something must happen 5 seconds later, or something must happen up to 5 seconds later. We load all of this language into the functionality. Temporal until is going to allow you to order events. Basically, when you need something to happen before before something else happens. So this is relevant, for instance, in electronics. Some events must happen in specific orderings, or maybe in aerospace when you have when you're launching a rocket and things must happen in a very specific order. When trigger is basically going to check if something if at the start of when something becomes true. When if in a causal relation, when like there is an implied relation, and then when the trigger happens, if the response happens. So yeah, so let me talk a little bit about this just to show a few examples, but I'm probably just going to show a couple of them. Yes, so for instance, here we have a very simple one. As I indicated, temporal always is going to is going to just check if something is always true. If it is not always true, it's just going to return false. Otherwise, if it's going to return true. The kind of syntax that we're allowing is kind of this. Within the 2-argument version, you can just put time and then any kind of Boolean expression here that depends on time. Or you can have also versioning with 3 arguments that allows you to, in the second one, to specify a specific time domain. Maybe you're not interested in the full simulation interval. Maybe you're interested in a specific time domain. So for instance, here's a very simple example. Yes, the one that we indicated at the start. In flight, when one engine is off, the distribution circuit must provide nominal performance. Right, so this is something that you can indeed wrap into temporal always. Basically, what we are writing here is when something is in flight and when the engine is off, just as the statement says, the performance should be must be nominal. So notice that we're here using all sorts of Boolean operations that are just part of the Wolfram language, and of course those are perfectly accepted in our functionality. So all the kind of Boolean operations that you can find. Other things that we support, things such as specifying, for instance, maybe your time domain, you want to specify it in terms of parameters. That could happen. So this is an example a very simple example for an RC circuit. We're just checking that the voltage before the time constant, the RC time constant, is always above above the value where the RC circuit reaches that, typically reaches that value. So we're just checking that for times before that the RC, the voltage is always greater than V0 over the Euler constant. So so you can specify your time domain with parameters in your model. You cannot specify variables evaluated at times that are necessarily t. So for instance, here, instead of writing V0 over E, I'm just writing the voltage at the time RC. You could also specify times that are not necessarily t, like for instance, maybe you want a time a little bit forward. So time plus something or time minus something, or in general, any function of time. So you can compare, you're not forced to use synchronous variables there. You can just use offset into times as well. So this allows you to cover all sorts of complicated requirements. Temporal sometimes is going to work very similarly. Basically, just going to check if something is ever true. And it accepts the same expressions. You can specify the 2 arguments. You have the two argument or 3-argument form. Here is a simple example. The aircraft must reach an operational service life of 100 flight cycles or 100 flight hours, whichever is more stringent. So here we have that statement. So we have temporal sometimes wrapping this statement. Either the flight cycles are greater or equal to 150, or the flight time is greater than 800 hours. Yeah, and obviously supports all sorts of the same kind of complicated statements that we had in temporal always. Of all the operators that I would like to look into, okay, maybe we can look at a couple of them. Temporal becomes, maybe I'll also show them. Temporal becomes, as I mentioned, focuses on when things start becoming true. So if you have a Boolean expression, you may be interested in the events related to when the things start becoming true. So temporal becomes just filters this to these events. In the statement where a requirement where you might be interested to use temporal becomes is, for instance, the angular velocity of a body in an active vector must become larger than 0.3 rads per second. So basically here we have the statement, the angular velocity of the object greater than 0.3. It's wrapped here by in temporal becomes, and then it's wrapped about in not. So this must never become true. So this is how we're writing the statement. And as you start using more of these temporal operators, when you ask for the report of the failure, we start decomposing the results more and more. So here we decompose it into first when the thing becomes true, and then here when it failed because we want it to not be true. So this is kind of a report that we're trying to produce for these kind of expressions. And then as more complicated, as the expression is more complicated, then the idea is for you to get a fuller report so that you can easily track exactly where things went wrong. Temporal between, here we have a simple example where you want to specify duration, like the one that I mentioned at the start. At no time the control signal should exceed 1.5 for more than 0.2 seconds. And that's what we're doing here. We're just wrapping that inequality into temporal between, specifying that we want to filter out the durations of 0.2 all the way to infinity. And we want that to not be true. So we want to never find this to be true for more than 0.2 seconds. And then we check it for this model. And again, as I mentioned, we decompose it. We filter the intervals where this became true for more than 0.2 seconds and show where this failed. Right. Then let me, here is an example. So if I left the slides available in the presentation, you can see all the other operators. Maybe I can look at another one before we start the questions and answers. Here we have the example of temporal delay. Whenever the controller is turned on, within 220 seconds, the room temperature must be in a specific range. So now we have to allow the possibility of a delay in this case. So here we have the controller being turned on. We just wrap it into temporal delay with the 220 seconds here specified. And we say that whenever this is true, this implies that the temperature is in the right region. And this must be true always because it's wrapped into temporal always. And then we just simulate, in this case, it also fails. So we decompose the expression a little bit more because it's a little bit more complicated. You can express here in the, you can use these help buttons to get a tooltip where we're plotting things a little bit, we're specifying what we are plotting on the plot. And you can see basically here we have the expression, the original expression, when the controller is on. Here we see when the delayed expression, so you can see that this true interval just got delayed, the 220 seconds here. Here we have the full response, so when the temperature is in the actual region. And basically we want that when the delayed expression is true, this must be true. But as you can see, this is a little bit, this is happening a little bit earlier than this, which is marking this failure interval in our results. So this is where things went wrong. So as we can see, if we allowed for a longer delay, for instance, then this would easily be satisfied. I guess we can just try it with 300 seconds, and then we can just validate that model. So as you can see, it's just simulating the model. First, building the model, simulating, validating, And then now it has actually successfully passed the requirement because we have allowed for a longer delay. Right. Um, Temporal until is about the ordering of events. This gets a little bit more complicated when you have two events, two phenomena, and then you're interested when something happens before the other, and you want to focus on those intervals where something happens before the other. Something. So basically, you have two expressions: the start and the end, two Boolean expressions, and then you're interested when the star happens right before the other one, when the star happens before the other one. So we're focusing in these intervals. Sometimes you want to focus in these events, for instance, in requirements such as whenever the controller is turned on until the temperature reaches a value in that range, the floor must input at least this amount of heat into the room. So sometimes you want to focus explicitly in those intervals and check exactly what's happening in those regions. So that's what we are allowing with this kind of expressions. But let me jump right into the conclusions. Here is one trigger as well. So you can just look into the function in to the slides. So again, so this is a functionality that we're working on. We want to provide all sorts of possible approaches to system modeling validation, and we want it to be updatable to all kinds of different workflows. We want to, at the same time, provide all sorts of comprehensive support for validating complicated requirements, but also we wanted to make it easy to use. So that's what we're looking forward to. So that's it. That's what I wanted to show. Let me see if there are any questions. It says here, can you create a trigger using the temporal functions that will be incorporated into an open electric switch, for example? Yeah, because I don't see why not. For sure. Definitely, we definitely want to cover the field of electronics. So I don't have an example here about with electronics, I think. But for sure, so for instance, you want to check that when your digital circuit, for instance, is returning true in a specific part of it, you want to check a specific requirement. So that's for sure a possibility. Or if you want something in an analog circuit, that should be also possible as well. So yeah, we're also particularly interested now into looking into applications, just to really focus on nailing this functionality, making sure that we get it right, so that we get it released in the 14.3. But this is already available in the WSN context. So this is as in the state that the slides are here with the initialization that I have here. This is something that you can completely run in 14.2 on your own. So it's all available. Right. I guess there are no more questions. Right, so I guess we can probably just stop right there and then see you next time.